Good morning, everyone. In this class, I'm gonna solve 6 problems to you on chapter 3. So, problem number 1 is about how we can use the difference on two pressure measurement to calculate the height of a building. So we have this example, guys. So we measure the pressure at the bottom. We find it 755 milligram Hg, and in the top we found the pressure 730 millimeter, Hg. So how we can estimate the building height if we know that the density of air in that area is 1.18 kilogram over meter cube. Very simple. It's depend on the concept of the pressure, which is rho GH. Rho GH. So what I need to know, I have the pressure in the bottom and the pressure in the top. I need to know the difference between them. Then I need to know how much air needed, how much air depth needed to to produce similar value of a pressure. Let's see how we can do it. Very simple. So the first, actually, by the way, we can solve this example by many methods, but let's see what is the book method. They calculate the pressure in the tube by kilopascal. So what we're gonna do, we convert rho GH to be in kilopascal, 97.3 kilopascal. In the bottom, in the bottom, 100.7 kilopascal. Very simple, right? Because we have this reading here. So very simple, guys. I know now the difference between the pressure in kilopascal. I know the density of air. So rho GH is gonna equal the difference between them. Very simple. So rho here, I know rho. G here, and this is just conversion. And I only the missing value is H. 100.7 minus 97.3. Done. So the height of this building is 288 meter or 298 meter. I think it's very clear and very simple. Right. Second example. Direct application on manometer, multi-fluid manometer. I have two pipes. In the left I have freshwater pipe. In the right I have seawater pipe. I connect them. I need to know the difference in the pressure between fresh and seawater. So I connect them with manometer, multi-fluid manometer. I have fresh water here, I have mercury here, I have air here, and I have seawater here. So we need to know what is the pressure, the difference between the two pipes. As I told you, just follow this rule. This rule is also described again here, guys. We consider this one as a 0.1 and this one as a 0.2, and we finish. P1, we see there is a drop. Here, this is the fresh water, there is a drop. So plus raw water, GH water, then mercury here, and the end is rising up, so it's minus. Then air, the end level of air is higher than the starting level, then it's minus raw air, GH air. The end level of seawater is lower than the starting level, so it's positive. All gonna equal B2 here. Finish. This is the golden rule. Read this, you understand everything. You can solve any question. Just after that, it's just like mathematics. Very simple. Just a small hint here. You see, I told you, because density of air is very little. It's very small if we compare to water and mercury. So you can ignore it. You can keep it as if you want, but it's up to you. You can just ignore it, but you must justify why you ignore it. Then B2 minus B1 is gonna be 5.3 kilopascal. Very simple and straightforward example. Right. Example problem number 3. Yeah, nice example. You see, guys, we have gas contained in a vertical frictionless piston cylinder device, as you see here. The area of this is 35 centimeters square and mass is 4 kg. Atmospheric pressure 95 kilopascal. And this spring can exert force of 60 Newton in the piston. So what we need to know, determine the pressure inside the cylinder. Very simple. I know the atmospheric pressure, I know the weight here, I know the extra force here. What I need to know? I need to calculate pressure. Very simple. I must calculate all the forces, convert it to pressure, then do summation with the atmospheric pressure, then it's fine. Then we can know the total pressure. Let's see how this example can be solved. Look, we do force analysis in y direction. We will know that we have F press spring downward, weight downward, and atmospheric pressure distributed here. This is the forces. The reaction is the atmospheric pressure inside the cylinder, upward here. So just very quick calculation. You need to know that we must convert this pressure to the force first, then you can do it as you wish actually, by the way, but let's follow this method. So we convert the atmospheric pressure to force, then plus weight plus F spring, then we divide all by the area. So P gonna equal 95 kilopascal plus these forces over the area. So the total pressure gonna be 123 kilopascal. Very simple, very straightforward example, right? Okay. Example number 4, which is application of a Newton's law. You see, guys, here we mix two concepts together here actually. You see, we have 500 kilogram load on the hydraulic lift here, as you see in the figure. And this is not water, this is oil. Density is 780 kilogram over meter cube. This is in the left side. In the right side, we have a thin tube. Wow. So we need to know how much the elevation here, H, should be, to raise, to qualify, to produce same pressure as the load. You can imagine that we can equalize this huge load by small raise in this thin tube. Why? I told you why, because the extra weight here will work in a small area, will produce same pressure as the pressure that is produced by the 500 kilogram. You see? So this is the concept of jack. So the solution is like that. We're gonna calculate the pressure here. This is the pressure. So we have atmospheric pressure here and atmospheric pressure. We're gonna gun with gun. So 500 kg over this area. Then we will see how much force need or weight divide by area. So we can do the calculation in 2 steps actually, by the way. So okay, so this is the pressure. As I told you, weight over area. Don't forget to times, weight is not mass. Don't forget to times by G. So we know that the gauge pressure is 4.3 kilopascal in the left side, that is produced by 500 kilogram here. Then this will equal rho GH. I know B, I know G, I know H, I know B, I know G, so I can calculate H. So we need about 56.7 centimeter. You see, just about 56 centimeter of water will be enough to hold 500 kilogram. It's about, so if we have like a car of 2 ton or maybe 2000 kilogram, we will need about 2 meters, something like that, right? So very interesting example. Yes. Okay. This example, let me see this example. Yes, problem number 5. Very interesting, also very simple. So we have, guys, we have like we have irregular shaped body, irregular, like, okay, are to be determined using spring scale. We need to know to calculate the volume of this irregular shape, right? So we know the body weight. We know that its weight is 7,200 Newton in air, and its weight in water 4,790 Newton. So now we need to determine the volume and density of the body. State your assumption. So I have this body. I have its weight in the air. I have its weight in the water. How can I know? How can I calculate the volume and density of the body? Very simple, guys. It's depend on the concept of buoyancy. You see, we must know that the difference between the two weights is equal volume of the shape times density of water. That's it. Finish. This is the concept. So first of all, I must know that FB, go to FB here, is gonna equal weight in air minus weight in mass. So this is the buoyancy force. Also, you need to know that we can know the mass easily by time the weight in the air over the G. This is mass. This is, you must be able to do that automatically. So we know that F buoyancy is equal rho water times G times V. I know now FB, this V, so I can easily get volume because I know raw water, I know G. So volume of this shape is equal 0.246. I get the mass, I get the volume, so I can easily go to calculate density. This is important equation. Okay, this is important equation. The last example for this chapter, we have ice block. We don't know how much the depth of it. We need to calculate the depth. But what we know that when we put this ice cube in the ocean, we can see only 25 centimeter over it. Right. So we know that the specific density of ice is 0.29 and the specific density of seawater is 1.025. Don't ask me what is specific density. It's density over 1000. So when we say it, seawater specific gravity 0.92, meaning that density, if we say specific gravity of ice 0.92, meaning that density is 9,920. Specific gravity of ocean 1.029, meaning that density is 1025, etc. So how are we gonna use this information to calculate the depth of the ice cube? Very simple and very straightforward. Let's see how we can do it. We need to know, we do like force analysis. Weight here for this. Weight of this immersed body is gonna equal the buoyancy force, right? It's known. This is known. So we're gonna do like that. We're gonna, what is the weight? It's raw body, the ice, G, V total, volume total. F buoyancy is raw fluid, G, V submerged. Okay, that's fine. Okay, so how can I do the calculation? I can know the V total up to, I gonna make equation because I know that I have 25 centimeter of the ice cube is above the sea water. So I can use this information to calculate a volumetric ratio. So guys, very easy. So take G with G, so you will see V submerged over V total is gonna be raw body over raw fluid. I know raw body, I know raw fluid. So this will be because we have same dimension, it's a cube. So it will be like H submerged to H total. I know H here, H submerged H total is gonna equal H plus 25. Finish. I have equation only one missing H. H is gonna equal 2.91 meter. That's it. I think it's very clear answer. Anyhow, this is the solved problems for this chapter. Please watch the revision class, watch the video, this video. If you have any extra questions, you can send me at my email. Thank you so much.